that we are recording. And take it away, Austin.
All right. Thank you all for having me and the Mel for organizing. So I want to talk about some lattice point problems today. Lattice point problems, they have a tendency to show up in numerous examples connected to number theory because number theory, we're often very interested in discrete things. So some famous examples include the Dirichlet divisor problem. Okay, we always see this at least in a basic form in an introductory analytic number theory class, where we all know the divisor function that counts the number of divisors of an integer k, and we'd like to estimate this divisor function on average when we sum it up to n. Okay, and geometrically, if you actually uh, think about this for a second, you're looking at the number of ways to write n equals xy for everything up to some capital N. So this is equivalent to finding the number of integer lattice points underneath the hyperbola xy equals n in the first quadrant. Okay, and so that's essentially how you go about it in an intro number theory class. You break up into nice regions where it's easy to count and sum up all your lattice points. And this shows up naturally in a couple settings we're interested in. For example, when you're estimating the mean square of the zeta function on the half line, okay? If you actually take the zeta function and you square it, and you look at the Dirichlet series, the coefficients of the Dirichlet series is the divisor function. And so sums like this have a tendency to show up naturally. Another famous sort of lattice point theorem with number theory implications is Minkowski's theorem, which gives us some necessary conditions for a convex set in Rn to contain at least one point of a lattice. Okay, this has, uses for all sorts of things, whether it be rational approximation, 2 and 4 square theorems, or if you're trying to bound the class number of a numbered field, classical bound to get there. Uh, and the problem I want to look at sort of as a model problem, and then we'll look at some sort of variations and other problems inspired by this, but sort of one of the classical problems I want to think about for a moment, just in some background, is the Gauss circle problem. So our goal is if I have some circle x squared plus y squared equals capital N, so we're dealing with a radius of square root n, we want to estimate the number of lattice points that fall inside of this circle. And so one way of sort of approaching this, at least for an elementary estimate, is for each lattice point inside the circle, you just identify it with a little 1 by 1 box having that lattice point at its lower left corner. And so each box has area 1, so each lattice point counts to 1 square of area, and so the total number of lattice points is just the combined area of all these boxes. And we can see the area of all these boxes together overlaps largely with our circle, so we can approximate our total number of lattice points by looking at the area of a circle. So, of course, then we want to know as number theorists, okay, how good is this? What's our error? Can we get some type of asymptotic? Well, on a heuristic level, if we're thinking about our error, each box we cross along the edge of the circle either overcounts or undercounts our area by at most one. Okay, so here we're cutting in the first quadrant, we cut off all these areas from all these boxes, and so that's all undercounting by however much area we leave outside. In the third quadrant, we do the reverse, we overcount by adding in white area. And so over under one for the number of boxes we cross along the boundary. And these boxes are fairly regularly spaced along the boundary, so we'd expect that the number of boxes we actually cross should be proportionate to the circumference of the circle. So our error is about our number of boxes crossed, which is about our circumference. And you can formalize that and actually get an asymptotic without too much difficulty. What we do is we just add two more circles to our picture. Okay, one where we expand our radius by a factor of root 2, the diagonal of the boxes, so that we're sure that every single box lies inside of the larger circle, and another where we shrink it by root 2 so that this circle lies entirely within all of our boxes. So then the original circle had radius root n, so the area of the smaller circle is pi times root n minus root 2 squared. And that's less than our number of lattice points. And then our upper bound is pi times root n plus root 2 squared. And so you expand these all out, you rearrange some inequalities, and we find that our error is at our number of lattice points minus the area of the circle, and that's at most 2 to the 3 halves times root n plus 2. So on the order big O of n to the 1 half. Okay, and so uh, this approach, or something very similar to this, is the approach Gauss took. I believe this was included in disquisitions back in the early 19th century. But since then, we found the circle problem and the divisor problem sort of go hand in hand. You make an improvement on one, that gives you an improvement on the other, and vice versa. And as we mentioned before, the divisor problem then connects to the mean square of the zeta function. And so anytime you can draw a connection to the zeta function, especially on the half line, now analytic number theorists get curious. So we want to try and see if we can get a better error term than this square root of n here. Okay, so the first result on this was back in 1906. Sierpinski brought the error term down to big O of n to the 1/3. But at least as far as I can tell, the most influential paper from this era was due to van der Korpet in 1923, who introduced his method for dealing with exponential sums that were showing up in the error term, and he got some power of n that was strictly less than a third. I don't believe he was able to actually give the power explicitly, but he got it less than a third. And since then, a number of authors have given us steady progress over steady decade. There's far more than I was able to list here, but for example, work of Klesnik, Ivanich, and Mazzocchi, and Huxley have continued iterating on van der Korpet's method and adding new twists here. And so the current record we have for our error term is big O of n to the 131 over 4/16 plus epsilon. That was due to Huxley in 2003. And so 131 over 4/16, that's about 0.3149. So I've gotten it down a little bit from the 1/3, but still some room there. As for what we think the error might be in the best possible, well, way back in the early part of the 20th century, Hardy gave us an omega result, and he showed the error term is at least omega of n to the 1/4. So we sort of expect something like n to the 1/4 plus epsilon is the best we could do, unless someone comes up with some uh, fantastic new way to come up with a third order term, or sorry, some second order term on that order. Okay. And in addition to sort of the geometry of lattice points inside the circle, this has a fairly natural arithmetic interpretation as a question about partitions into squares. So if I let R of n be the number of ways of writing n as a sum of two squares, x squared and y squared, where x and y both lie in n, then the number of lattice points in the first quadrant is just the sum of R of n up to the capital N, where our circle has radius root n. Okay, because anytime we take, some x squared plus y squared less than that, it's going to give us the way of writing some integer less than that. Okay, so if we come up with an estimate for the circle problem in one quadrant, then that's the same for an average of R of n. Okay, uh, so that's what I have to say about the circle problem. But as soon as you start thinking about this in terms of partitions, and sums of powers, you can then sort of tweak this and come up with a bunch of other interesting problems. Okay, so a bunch of other things come up naturally. For example, you might ask, what if instead of thinking about sums of two squares, you think of sums of two cubes? Okay, this didn't have a nice picture of a circle because the overall curve is unbounded, but if we just restrict to the first quadrant, this gives us a bounded region in the first quadrant by some polynomial level curve at x cubed plus y cubed equals capital N. And so when we average this function in R23, counting the number of ways of writing n in two cubes, you can do sort of similar heuristic and get that it should be a main term on the order of n to the 2/3. This would correspond to the area of that region bound in the first quadrant. Plus, your error term should be on about the order of n to the 1/3 is what you'd expect. Okay, and as for improving this, going beyond just sort of the area scaling heuristic like we saw for the circle, one of my advisors, Bob Vaughn, showed back in 2020 that you can actually free up the second order term, this n to the 1/3 right here, and you get an average that looks like, again, this ratio of gammas here, n to the 2/3, that's where it comes from the area, minus an n to the 1/3, and then you get an error term on the order of n to the 2/9 log n to the 1/3. Okay, so that's how you deal with cubes. What about larger powers like kth powers? Okay, so we let R2k of n be x to the k plus y to the k equals n for natural numbers x and y. Then another one of Bob's students, Pengyong Ding, showed back in 2022 that when you sum up this average, R2k of n, you get, again, this sort of similar looking formula, this ratio of gammas times n to the power of 2 over k minus n to the 1 over k, and your error term is on the order of n to the k minus 1 over k squared. Interestingly, it's pretty much as soon as you get to powers that are larger than 2 that the logs start disappearing from the error term. Okay, so that's 2 squares and 2 cubes. Uh, but as I've been looking at this, I've found a lot less on other polynomials and other forms for these sort of similar averages. So I've taken up some of those and I have a couple of results to share. So what I'm now going to do is I'm going to let R sub f of n be the number of ways as representing n as some f of x, y for two natural numbers x and y, where f is going to be some nice polynomial. And the first theorem I have to share is about these two forms. So I have a quadratic form x squared plus xy plus y squared, sort of the nicest, first example to look at where we have an off-diagonal term. Okay, and so when you sum up this function on average, you
Awesome.
get a constant.
There's a comment in the chat for you. Can you read it for us?
Oh, yes, let me see if I can. Hold on, I think I'm in full screen, so that's not.
I can just say it.
Yeah,
Say,
sure.
I think that Van der Korpel's work explicitly states the 33 over 100 um, mm, exponent.
Oh, does
This
it?
was a divisor
Okay.
problem.
Thank you. Yes, I tried to pull up some of these old papers, but I couldn't read German, and so I was looking at a Littlewood paper that came after, and Littlewood just said, I believe Littlewood's paper just wrote some constant strictly less than a third. So thank you for that. Okay. Back to this here. I'm going to go back to full screen. Where do we go? There it goes. Okay. Uh, And so we get this constant C2 times n minus n to the 1/2 and an error term n to the 1/3 log n to 2/3. Where this C2, that's a constant we can calculate not too hard. That sort of corresponds to an area. I'll talk a little bit more on that in a second. And then for a cubic form, so for example, a nice simple cubic form we can look at with some off-diagonal terms is this x cubed plus x squared y plus xy squared plus y cubed. Okay, and so when we sum that all up, we get some constant C3 times n to the 2/3 minus an n to the 1/3 plus this error term here. We get n to the 2/9 log n to the 2/3. And the C3, we can write it out explicitly in terms of an integral. It's just kind of a messy integral that doesn't go nice on the slide, but we can calculate that constant if we want to. Okay, so there's a couple forms there, and to also give a result, for example, for mixed degrees, so we saw 2 squares, 2 cubes, and beyond, but if we want to mix up some degrees, and I'll even throw in some coefficients here, so I'll let a and b be positive integers, and little a, little b be, I guess I should have just said a and b can be bigger than 0, and little a, little b greater than 1. Um, so I have this ax to the a plus by to the b, and I set up this r sub f a b of n. I should have put the end of n there, so excuse that typo. Then I get an expression that looks like this. So my main term is on the order of n to the 1 over a plus 1 over b, and I get this uh, coefficient out front. That's just this ratio of gammas minus this coefficient. I get an n to the 1 over a and a minus n to the 1 over b, and then my error term comes from this expression here, and whichever term dominates just depends on sort of the relative sizes of little a and little b. Okay. Uh, and like before, to get in addition to having it as looking at an average of ways to write a number as some polynomial, you can also think of it as lattice points bound by the level curves of whatever polynomial you're adding. And if you look at sort of the structure of all these asymptotic formulas we've looked at, this c times n always corresponds to whatever the area is of the level curve f of xy equals n. Okay, and so that's where that constant c always comes from. And then this minus n to the 1/2, that sort of shows up because we're not counting our axes. So in the circle problem, we didn't see, any sort of second order term show up because we sort of looked at the full circle and we didn't throw any of the axes. So this shows up when we're not looking at the axes. We sort of count it minus 1/2 of the area from each axis. And then those all would come back to complete and eliminate that term in the full circle problem. And then, however, well, we can get the error by controlling things that happen along the boundary. And so when we have this picture in mind, that sort of suggests a natural plan to attack this. So for something like x squared plus xy plus y squared equals n, a form like this, well, I can solve explicitly for one of my variables, say y, and I just say y is this function g of x, where I can solve it using a good old-fashioned quadratic formula like we're back in high school. Okay, and so then if we look at all the lattice points in each one of these columns, the number of lattice points in a single column is just the floor of this function g at whatever input I'm at along the way. So if I just sum up the floor of my function g, then that gives me an estimate for my total number of that gives me a reasonable estimate for my total number of lattice points. Okay, and the better I can control that, the better an error term I'll get. Uh, so that's a nice approach. The floor function can be somewhat finicky. So to deal with some of the things that come from a floor function and try to get a better control on it, we're going to look at the first periodic Bernoulli function. Okay, the first periodic Bernoulli function, it's just this sort of sawtooth. It's x, and we subtract off the floor of x, so it bumps up and then drops down, and it just keeps increasing linearly and dropping off. And then we shift it down by a half so that it's 0 on average, because that's a nice property to have. And so when we look at this, we can rearrange our floor into x minus a half and then minus the first periodic Bernoulli function. And the reason this is nice is it sort of splits the floor function up into a smooth part. X minus 1/2 is really nice, well-behaved, smooth, and linear. And so we have all sorts of techniques from calculus and analysis to deal with that. And then this periodic part, this b1 of x, which we have all sorts of techniques from Fourier analysis to deal with periodic things. And so my sum, when I'm summing up the floor of g of n's right here, I just split that up into, I get this smooth sum adding up g of n minus root n over 2. That just comes from the number of 1/2s I subtract and an O of 1, just because we're dealing with a floor there. And then minus the sum of this Bernoulli function of g of n. Okay, and so I deal with each of these parts. So the smooth sum you can deal with fairly easily, just make an Euler-Maclaurin sum argument. So the sum g of n, if you apply Euler-Maclaurin summation, you get an integral of g of t dt plus, I'll look around the boundary, g of n to the 1/2 minus g of 0 divided by 2. And then you integrate the derivative g prime against the b1 of t. Okay, so the first integral, that's just the area of our region. Okay, the g, again, remember that was just the height of our level curve at each point. And so when we integrate that, we get our total area. And so for a function like 4n minus 3x squared to the 1/2 minus a half x, that's not too hard of an integral to calculate. You could even give that to a Calc 2 student as a trig sub on their homework, and you get a constant like this pi fourths plus 1 over 3 minus 3/4. So that's where that comes from, and that's the source of our main term. In the second, g of n to the 1/2 and g of 0, that's sort of the two ends of our level curve. So at square root n, that's where our level curve touches down and meets the x-axis. So that's going to be 0. And g of 0 is square root of n, just by this sort of symmetry. So that's where we get a minus square root n. And then the last integral you can deal with, you integrate it by parts, and without too much effort, you can show that it's uniformly bounded independent of n. So That's big O of 1. Okay, so this smooth sum gives us our main term, and so now all we need to deal with is the periodic sum. Okay, so B1 has a nice, well understood, nicely behaved Fourier expansion that we can truncate at some point with an error term, and then all these coefficients we have nice bounds for. So what we do is we sort of take, if we want to look at the Bernoulli function of this g and sum it up to n to the 1/2, uh, we Fourier expand that, and then we also sort of break things into a dyadic range, uh, where we sort of, it looks like a mess on the slide, but we have a sum inside of a sum, and then this T of M8 here, that's another smaller exponential sum. Okay, and so this innermost exponential sum that shows up here and in this error term, uh, those we can deal with by borrowing this lemma from van der Korpet. Okay, so this lemma we borrow from van der Korpet says that if f is a real valued function with a continuous second derivative on AB, excuse me, and we have bounds for our second derivative above and below, then we can bound our exponential sum in terms of the bounds for the derivative and the length of our interval. So when we do that with the innermost exponential sum that appears back on this slide, we get a bound that looks like this for our specific g of n. And then we make some choices with where to sort of break this up and where to truncate. And the overall thing, when you just sort of sum everything up, we get the B1 g of n is asymptotically less than n to the 1/3 log n to the 2/3. And so that's our dominant error term. So when we combine this with the main term we found earlier, we get an asymptotic formula for r sub f2 of n as c2n minus square root n, and then our error term is n to the 1/3 log n to the 2/3. Okay. So that's how we prove it for something like f2, this x squared plus xy plus y squared. And then the other two, I mentioned the cubic form and the mixed, the ax to the a and by to the b. Those follow quite similarly. And really, anytime you have some nice small degree thing where you can easily solve for one variable in the level curve, you can apply a similar method and get a similar asymptotic. Okay, there might be some symmetry tricks you can do to save in some areas, but they all look sort of similar to that. Okay. A sort of next question you might ask is, what if instead of looking at lattice points bound by a curve in 2 dimensions, if we wanted to sort of have a third variable in there and deal with lattice points that are bound by some polynomial surface with 3 variables or even a hypersurface with more? And that's a bit trickier to isolate because now even if you solve for a single variable like we did here, you're still dealing with a sort of 2-dimensional sum. Um, but we can treat it in some special simple cases. For example, if our polynomial we're dealing with looks like, one of the forms we've established an asymptotic for, and then we just add on some power of z, maybe with a coefficient c. Okay, so if we start looking for the number of ways to represent uh, an integer n as some f of x, y, z, for example, maybe x squared plus xy plus y squared plus some z cubed, uh, then we can get at least these simple ones adding powers of z. And the way we sort of go about that is we just sort of count z can take any value from 1 up to n to the 1/3. And then the number of possible choices for our x and our y, uh, we can use our asymptotic for rf2, or sorry, r sub f2 of k. To count those for some k that's up to n minus z cubed. So if you index all the possible choices for x, y, and z, it looks something like this nested sum, and this inner sum right here is the exact average we just established an asymptotic for. So we plug our asymptotic inside of the sum, and then from there, everything in the sum is smooth, so we can do a nice sort of similar Euler-Maclaurin argument, and we get a formula that looks something like this. Some ratios of gamma shows up, and we get a nice error term on the order n to the 2/3 log n. And in general, when you add a power, the error term just tends to go up by 1 over whenever that power is. Okay. So I'm a bit tight on time, and that's all I had prepared for today. So thank you all for having me, and I'm happy to take any questions.
So first of all, do I understand correctly that if we allow the variables to be integers, then the second term in asymptotic formula for x squared plus xy plus y squared disappears?
Um, I think it would if we allow the complete. I have to think a little bit because so the first and third quadrant certainly are symmetric. The second quadrant looks slightly different. I haven't actually tried to do the full thing with both positive and negative integers. I've only done it with positive integers. But yes, I would expect a second order term like this generally accounts for the fact that we're removing an axis. And so that would remove.
Mhm.
Just probably have to count the sums in the third and fourth quadrant. They would show up a little bit differently than they did for the first and third quadrant.
Secondly, so there is a formula for RF2 of n as a sum of a Dirichlet character of divisors of n. If we apply this formula and then use a sort of modified hyperbola method, then I think that we can prove something similar to the Huxley bound, right?
Uh, it's very possible. I know there's a lot of there's a lot of ways I think you can certainly come at this more advanced. So this lemma from van der Korpet is sort of the one of the simplest things you can do building on van
Mhm.
der Korpet's method, and there's a lot deeper you can take it. This is all I've done so far with these types of problems, but yeah, I imagine you can certainly get something much lower, like a Huxley bound, the further you take this.
Okay, so at least I believe that we can get a lot closer to Huxley bound from just general formulas with sums over divisors. Thank you.
Okay. Yep. Thank you.
The questions for Austin? Not this. Thank our speaker again. And the problem session will start momentarily.
As soon as somebody has a problem.